In this world, there are too many unknowns. Some are close at hand, some are relatively distant, and there are even unknowns that we are unaware of. When we humans acquire enough knowledge to pose a question and solve it, new questions will inevitably arise. What is the universe composed of? What is truly fundamental in the reality we perceive? In 400 BC, the Greek philosopher Democritus proposed that everything is made up of atoms, which he believed were solid and indivisible. 2,300 years later, in 1897, J.J. Thomson discovered something smaller than the atom, called the electron. In 1912, Ernest Rutherford discovered that atoms have a nucleus. Scientists then found that the nucleus is composed of protons and neutrons. At the time, these were considered the fundamental building blocks of all matter. It wasn't until the 1960s that we discovered protons and neutrons are made up of even smaller particles called quarks. These two types of quarks are the up quark and the down quark. Today, everything we see is believed to be composed of these particles: electrons, up quarks, and down quarks. These are the components of all atoms. They make up your phone, your desk, your skin, the flowers and plants you see, and everything else. The only question is, how do we know that electrons and quarks cannot be divided further? Just because we can't detect it now doesn't mean we won't in the future. Physicists have known for decades that these particles are not truly fundamental. The best theories in physics tell us that, in fact, there are no particles at all. Nature is made up of fields, and the universe, at its core, is composed of many different fields. What we call particles are merely waves in these fields. So, what exactly are these fields? What do they tell us about the nature of reality? The concept of particles, even those in the Standard Model, is not the true essence of the universe. Particles are fictional. They are just a convenient way of describing things, not the best understanding of the universe we have today. The fundamental nature of the universe is not particles, but fields. These fields are fluid-like substances that can be disturbed, vibrate, and be excited. What is a field? Mathematically, a field is something that can take a value at every point in space. From a physicist's perspective, fields are not made up of anything else. Imagine a fireplace in a room. Every point in the room has a temperature value, and this is a temperature field. This is similar to the fundamental fields of the universe. These fields are everywhere in nature, and you cannot escape them. If you take a sturdy metal box and remove everything inside, all the gas, all the atoms, all the photons, what remains in the box is what we consider a vacuum, an empty void. But in reality, this vacuum is filled with fields that are constantly moving and changing. Heisenberg's uncertainty principle means that quantum fields cannot be still. Instead, they constantly move, vibrate, and change their values over time. This is a computer simulation of a vacuum, where all the bursting bubbles you see are disturbances in the vacuum. Particles are constantly being created and annihilated in this void. These particles are actually excitations of fields throughout space. You can see these excitations in the world around you. In fact, what you can see are excitations of just 4 fields: photons or light, which are vibrations in the electromagnetic field, electrons, which are vibrations in the electron field, and up and down quarks, which make up the protons and neutrons in atomic nuclei. These are vibrations in the up and down quark fields, respectively. Surprisingly, everything around you, your phone, your desk, the flowers and trees, the ground beneath your feet, is made up of these 4 fields. But the universe has more than just these four fields. In fact, the particles we designate in the Standard Model are actually excitations or vibrations of their own fields. Including the Higgs field, there are a total of 17 fields. Note that spacetime itself is also considered a field, but so far it cannot be incorporated into quantum field theory. This would be the 18th field. What we call particles are actually waves. These waves are not like ocean waves. This is just an analogy and a visual aid to help us understand. Can we see these fields? Of course not. Fields are invisible and intangible, but you can get a visual sense of them by placing a magnet near some iron filings. The lines you see are actually the magnetic field lines altered by the magnet. Another way to visualize fields is to imagine the universe filled with water, as if we live in an ocean. Now imagine this cosmic ocean filled with about 17 different fluids, each with a different color. This might look spectacular and bizarre, but it somewhat resembles what our universe is actually like, except you can't see these fields. Why is field theory better than the concept of particles? Field theory addresses the key issue of action at a distance. For example, in Newtonian gravity, we must accept that the sun's gravity somehow affects the Earth, which is 150 million kilometers away. How can something influence something else so far away without any contact? This is action at a distance. Even Newton thought action at a distance was absurd. He said it was hard to imagine that inanimate matter could act on other matter without any medium or contact. Einstein's general theory of relativity eliminated the concept of action at a distance by replacing space with something called spacetime. Spacetime is a field that permeates all of reality, and Einstein mathematically proved that gravity is actually due to the curvature of the spacetime field. Anything that happens to a particle anywhere in space is controlled by what happens in the field near the particle. For an effect to propagate over a distance, it must locally affect its field, then propagate from that local point to another distant point, and then locally affect the field at that distant point. This is similar to how waves propagate in water. If you throw a rock into water, waves will spread from the rock to the shore and affect the sand on the shore. Fields can also explain how particles are created and annihilated. For example, when a neutron decays into a proton, an electron, and an antineutrino, how does this happen? Was the electron hiding inside the neutron? Where did it come from? Fields have the property that if you hit them hard enough, they can release vibrations or energy, and they can also influence other fields. In this decay, the energy of the neutron's quark field can transfer to the proton's quark field, as well as to the electron and antineutrino fields. Moreover, particles and antiparticles are excitations of the same field, described as equal but opposite excitations of the field. They have two opposite wave representations, and when these waves come together, they annihilate each other. You are influenced by these fields every day. When you use your phone to call someone, you are exciting a field that affects the electronic device in the person's phone. This is action at a distance in practice, but it is not action at a distance in the classical sense. Your phone creates an excitation in the electromagnetic field, which propagates from you to a cell tower and eventually to the receiver on the other end. But there seems to be a dilemma here, as many people already know that quantum mechanics is about discrete things. It is not continuous. This is why it is called quantum. But fields are continuous, not discrete. Thus, there seems to be a conflict between the concept of particle discreteness in quantum mechanics and the continuity of fields. So how are these two views reconciled? The combination of field theory and quantum mechanics is called quantum field theory, or QFT. Essentially, All excitations of fields can only occur in discrete energy packets. The energy of a wave is determined by the mass of the particle. What is mass? The mass of a particle is the energy required to vibrate its field. If you recall, energy equals mass, as shown in Einstein's famous equation, E equals mc squared. A field will not accept energy below a certain threshold, but if you hit it hard enough, you can create a particle. The discrete units of energy that a field can accept are what we call the rest mass, or energy of a particle. In the field, this is the minimum energy required to create a particle. For example, when the electron field is excited by 0.511 MeV, an electron is created. This is the mass of an electron. If you add 0.4 MeV of energy, no particle is created. If you input 1.1 MeV, 2 electrons are created, and so on. This applies to all particles. All the electrons in our human bodies are waves in the same fundamental field, so the field is the foundation, not the electrons around us. There are also up quark and down quark fields. All the atoms in our bodies are made up of particles, and these particles are just ripples in these three fields. Every person on Earth shares the same foundation. In fact, all other planets and the Sun are also in the same field. We are essentially made up of ripples in the same three fields that exist throughout the universe. Although there is no evidence that the ripples in my field can communicate with the ripples in your field, it is a continuous field, and everything is connected to it. However, fields do not tell us everything. They do not tell us what dark matter is, what dark energy is, how the Big Bang happened, or why there is more matter than antimatter in the universe. So science still has a long way to go. What is the relationship between the waves in fields and the probability waves of quantum mechanics and the Schrödinger equation? When we say an electron is a particle with position and velocity, this is wrong. Not because we cannot measure its position and velocity, but because there is no such thing as position and velocity. Everything is a wave function, spread out over all of space. It only tells us what the position and velocity would be if we chose to measure them. For example, the shape of the electromagnetic field is the wave function of a photon, and the shape of the electron field is the wave function of an electron. The wave function is what truly exists. When you observe an electron, you do not see the wave function because it has already collapsed into a discrete value, which can be predicted by the Schrödinger equation. These fields are constantly vibrating and modulating, and when you measure them, they collapse into individual packets of energy called particles. So quantum mechanics tells us that fundamentally, reality is different when you measure it and when you don't. Every particle in the universe is a tiny ripple in an underlying field, shaped into a particle by the mechanisms of quantum mechanics at every point in space and time. Vibrating quantum fields are the fundamental building blocks of nature. Therefore, the age-old question of whether light is a particle or a wave can be answered. The answer is that it is a wave. When we measure the wave, what appears is a particle. Who discovered fields? The British scientist Michael Faraday first proposed the idea and used the term field in his notes in 1845. Are fields real things, or are they just mathematical constructs? Even though fields are not made of any known physical substance, they are considered real physical entities because they exist in space and possess energy. Moreover, their properties can be accurately calculated and predicted through experimental results. Now we ponder a question. Are these fields the most fundamental foundation of the universe? To some extent, fields are the most fundamental foundation because they represent the limit of our understanding. But it is also possible that these fields are just approximations of a deeper reality. Ultimately, there must be some more fundamental reason why these fields have the properties they do. Why does the electron field require a minimum of 0.511 MeV? Why do they follow mathematical rules? Will we ever know the answer? It is also possible that we are not asking the right questions, or that the direction of our research is fundamentally wrong.